map. This question wants us to build a synthetic map. I'm recording now. So we have compound X, and when we do hydroboration oxidation, we get this product, 2,4-dimethylpentane 1-ol. The reagents for hydroboration oxidation would be 1, borane and THF, and 2, sodium hydroxide and hydrogen peroxide. We also have hydrogenation produces 2,4-dimethylpentane, so that would be H2 and PT. So there's your 2,4-dimethylpentane. Okay, so what this means is X is an alkene, right? And we need to figure out what X is. So I think that X is this. (2,4-dimethyl 1-pentene), right? Because hydroboration oxidation gives you an anti-Markovnikov alcohol, right? And H2PT would give that, right? So both of those things are true. And so then they want to know what happens when we treat it with an aqueous acid, right? So in other words, if we do acid catalyzed hydration, what should we get? So H2SO4 and H2O, right? And so when you have H2SO4 and H2O, it's really present. The acid is all present as hydronium. And the pi bond is going to act as a base and do proton transfer to create a carbocation. Now, the carbocation could go there or there, and it's going to make the more substituted one, right? That's more stable. Right, so our carbocation is going to be on carbon 2. In this case, we are already tertiary, so rearrangement is not going to buy us anything. If we did a 1,2 hydride shift, for instance, that would give us a secondary carbocation. So we're not going to do rearrangement. But we have a water that can act as a nucleophile, and it'll attack in that tertiary position, which gives us the protonated alcohol. Right, and then to deprotonate the oxonium, another water molecule acts as a base to do that proton transfer. Right, so this first step, proton transfer, there's two curved arrows. The first one looks like nucleophilic attack, but it's attacking a proton. And then the second one looks like loss of a leaving group. Right. And then the second step is nucleophilic attack, right, with the water acting as a nucleophile. And the third step is proton transfer. But we could get rearrangement if the carbocation formed here was secondary and not tertiary. It's just that we're not going to get a more stable rearrangement product there. The pi bond acts as a base, right, and it takes a proton. That gives us this carbocation. And say that one is the proton that came from the acid. right? And the reason the proton doesn't get added there is because that would make a primary carbocation, which is less stable.